Okay. Um, all right. I am absolutely thrilled to introduce Jason Young, who I've collaborated with for, well, since 2020, when we met at the AAS in Hawaii and at the giant poster of the Rubens Galaxy is one of both of our favorites. So Jason has been a great collaborator, and he's going to tell us about star formation in the low surface brightness universe, which is coming with the Rubin Observatory. So take it away, Jason, if you're ready.
All right, thanks for the introduction. And I'd also like to start by thanking all of my collaborators, including Benna. Um, Star formation occurs in a vacuum, but science doesn't. And I couldn't have done it without all the folks that are on this list, as well as many others. And I'll highlight a few of their components of the project as we go through. I'd also like to acknowledge the fact that a lot of the data for this project was collected on the unceded lands of the Apache and Humanos peoples here in the US. Um, and without that data, this project wouldn't be possible either. So, a few of you might have noticed one of our objects actually hiding in the title slide. We have this group of galaxies here. They're all late type spirals, but two of them, the two brighter ones, are high surface brightness galaxies. But the one at the bottom is one of the kinds of objects that we're going to be looking at today, a low surface brightness galaxy. So when people ask me about this, I have to emphasize that this is not a bimodal distribution. Spiral galaxies, span a range of surface brightnesses. The ones that are overrepresented in surveys and heavily studied, and candidly, the ones that make the really gorgeous images are at the left, the high surface brightness spirals. Um, and they're the most common type of massive galaxy. But if you sort of go along the continuum here toward lower surface brightness galaxies, they're also fairly common, just more difficult to detect. General trends are that they are often, gas rich. They tend to be more isolated. They host very little star formation, but there's also no clear distinction. And for this project that we're going to be hearing about today, we have a soft limit of 22 magnitudes per square arc second of what we consider to be an LSB galaxy, but different groups will kind of draw that line in different places. If you're interested in the ultra diffuse galaxies that we see at the centers of clusters, those you might think, well, those are gas poor. What are you talking about, Jason? That's kind of a different beast and also a different talk. And those are also a fascinating class of objects. But they also don't present some of the paradoxes that we see here. So a tiny bit of history. In the 1970s, there was this thing called the Freeman Law, where they noticed that the surface brightness distribution of galaxies had this sort of, almost Gaussian look to it. And people realized immediately that it peaked at around the level of surface brightness that you see from light pollution in the darkest locations. And so by the 1990s, there were aggressive surveys to try to, find the galaxies hiding behind the sky. And there was even speculation that there could be this extremely large number of galaxies that change the baryon content of the universe. And maybe the galaxy distribution was, as seen in this figure here, almost flat at surface brightnesses much lower than 22 magnitudes per square arc second. That speculation was mostly put to rest later on, but you can see why they might have thought that, right? Where our ability to detect an object is less related to its total brightness and more related to its contrast. If you take the same amount of light and spread it out, we're much less likely to be able to detect that same source. So by the early 2000s, surveys had gotten very good, and our knowledge of the sensitivity function was excellent. And by that point in time, we could sort of put this idea to rest that there were, enough galaxies hiding behind the sky to change the baryon content of the universe. Low surface brightness galaxies are actually common with estimates of maybe around 10% of the field galaxy population, but they don't totally change the baryon budget. And they're also not a significant part of the luminosity budget of the universe. So my interest in them is not because they're, this universe cosmology breaking population that totally flips our understanding of galaxy evolution. Here's for comparison, the star forming main sequence, and we see that they are more or less within the cloud, just sort of hugging the lower envelope. They're relatively low specific star formation rates for the masses that they have. So my interest is to try to learn about the population of galaxies that we already have by looking at the extremes of the distribution, where there's a lot of interest at the high end of the distribution, these starburst galaxies that are forming stars really quickly. What are the physics like in those objects? And I think that's fantastic work. And I've actually authored a number of papers that look at, say, quasar host galaxies, a few of the objects even shown here. But I think there's also, by the same token, a lot to be learned by looking at the low end of the distribution, the 2 sigma outliers at the low star formation rates. What physical conditions lead them to be that kind of galaxy? If we can understand that, it tells us about galaxies in general. So a summary of where we're going with this talk. What physical conditions cause a galaxy to become a low surface brightness galaxy? What connection might they have to other types of galaxies? Do they kind of walk back and forth? How do they evolve? And maybe the most important, can we use them as laboratories to improve our understanding of star formation in general by looking at star formation in the low density environment, the same way that folks are looking at, galaxy mergers and starburst galaxies to try to understand star formation in the high density environment. So I want to get into the science by starting with a kind of a family photo here, where these are most of the objects from the sample that we're working with. It's not a huge sample, but this project is designed to take an in-depth look at a small number of objects, which is a really good complement to the massive surveys these days, which cover thousands and thousands of objects. So we're going to just get a really detailed history on some of these nearby galaxies. I plotted them surface brightness against absolute magnitude as a proxy for mass, and they span a range. This is not a homogeneous category. At the high mass end, we have objects that are in a similar mass class to the Milky Way. At the low mass end, we have dwarfs, and then we have objects in between. For me, the most interesting quadrant in this plot is the quadrant in the lower right, where you have a massive object, but still with a low surface brightness. And it's somewhat difficult to populate that quadrant, not because there aren't objects in that quadrant, but because observing them and doing a detailed study like we're doing takes kind of a ridiculous amount of telescope time. I have one object that's kind of hanging out in that quadrant right now, and that's an ongoing project to fully understand that object. But this is something where I'm hoping that deeper observations, say from Habitable Worlds Observatory or Rubin, might be able to help us out in the future. One interesting thing about this diagram here is I've scaled all the objects to a similar sky scale. So this is what they would look like if you could actually put them physically together at the same location in space. And as you can see, they really do span a range, not only in surface brightness, mass, but also in size and morphology. And so it may be that the underlying thread between them is all common, but it could also be that this really is a heterogeneous population in terms of causality too, something we're going to find out. So To understand the formation mechanisms for these objects, we are putting together a multi-wavelength, multi-instrument spectral energy distribution. The backbone of the SED is coming from ground-based optical spectra that are IFU spectra, so we get the spatial and spectral information. That is tuned to encompass a lot of the intermediate age indicators in the sort of blue optical spectrum. The H delta line, the Balmer break, the general shape of the continuum, stellar absorption lines, things like that. But to give that spectra the maximum leverage to determine a formation history, we're also going to pin the SED at two ends. On the left with ultraviolet imaging from the SWIFT and Astrosat space telescopes, and on the right with IR observations, partly coming from the Spitzer IRAC database, but then also partly coming from K-band observations that I'm actually going to be collecting in December as part of the Williams College chair on the Apache Point Observatory in New Mexico. So the IR observations constrain the integrated star formation history, that is to say, the stellar mass, and the UV observations in tandem with optical emission lines constrain the current star formation. And with those 2 points constrained, we actually can work out a lot of the details of the formation history. A little bit about the IFU here. So this is mostly coming from the McDonald Observatory, which is, we're moving into an era of IFU observations in astronomy. They're becoming really common. And so I want to sort of spread the word. If you haven't used an IFU, they're fantastic instruments. This one puts a bundle of optical fibers at the imaging plane instead of a detector, and then feeds all the fibers down to a spectrograph. So we get a spectrum at every point in the image plane, and then we can reconstruct a 3D spectral cube because we know where the fibers are, and then cap it at both ends with the UV and IR observations to create the full SED. There's a lot of tools out there right now to fit star formation history to an SED. We're also living in a great time if you want to work on that kind of project. You can include all kinds of effects, AGN if you like. You can include dynamics, things like that. For this particular project, we're fitting the SED as a composite of synthetic spectra coming from the Pegas project, the Pegas spectral synthesis project. And if we know the relative contribution of the spectra that correspond to stellar populations of different ages, then we can use those relative contributions as a history and say that that's basically the formation history of every spaxel within our data cube. There are limitations, of course. Probably half of you are thinking about, well, what about dust reddening? It's a nonlinear parameter that has to be fit. What about gas phase ionization that also affects the line ratios? Another nonlinear parameter that has to be fit. So the devil's in the details, and I'd be happy to chat more about this. But the idea is that if you can decompose the observed SED into component spectra that correspond to stellar populations of different ages, then you know the formation history. All right, so I want to actually show some results. Let's focus on the first object in our sample. It's a Milky Way mass LSB galaxy, not an extreme member of the population, but well below that 22 magnitudes per square arc second in B band. That's the soft limit for our project. When we decompose its histories, or the history of every region within this object, because we have the spatial information from the IFU, and do an azimuthal average, we can generate the star formation plots on the right. So the colors going from red to purple correspond to the different epochs in this galaxy's history. And then we've azimuthally averaged them so we can plot them as a function of radius. On the right, we've taken the history of every spexel and basically created a synthetic UVB image, so Johnson UBV filters, to get a visual representation of this object as it would have appeared at different points in its history. There are a lot of limitations behind this, so a lot of asterisks on visual representation of what it would have looked like in the past. Let's start off with the fact that we can't correct for orbital motion. So things are moving around, obviously, over billions of years. The stars have gone through many orbital cycles. We can't unwind that. So we're showing them as they are, or at their current locations. It's an image of the stellar population at their current locations. Second caveat, you'll notice a bunch of holes in the image. I punched out areas where there are either foreground stars or background galaxies. And then third caveat, we're doing a best estimate of what the effective dust would be to try to create a realistic image. With those caveats aside, this is not a simulation. This is a data-driven recreation of the appearance of the stellar population over the history of this object. So what do we learn? Well, in the earliest time step, we see a burst of star formation at the center of the object. On the left, we see that sort of dark red curve that basically plummets after about 1 kiloparsec. That'll be really important near the end of the talk. So put a pin in that early burst of star formation in some objects. Interestingly, the core of the galaxy goes quiet after that and never really fires up to the same level that we see in the first time step. It actually goes through kind of the middle row in the image on the right shows what I call the dark ages for this object, where it doesn't really do a whole lot. But then in the last few 100 million years, star formation erupts kind of along the edges of the object, where it's building stars near its perimeter, and it's very patchy, it's very sporadic. But interestingly, it did rise to a level that it would have been considered a starburst around 50 million years ago. So we're actually seeing it right after, as we see it today, it's right after a starburst, which is a little bit of a paradox because this is a low surface brightness galaxy, and it doesn't have the nature of that category is that it usually has a very low star formation rate. So what this is saying is that galaxies can kind of walk back and forth between categories as they evolve, and we shouldn't think of these as sort of strict limits. But the bit where it's forming stars near its edges is also a really important point, and put a pin in that. That's going to come up later too. I want to talk a little bit about the importance of the ultraviolet observations in the SIG. So our program has been lucky enough to get a lot of time on the Swift telescope and the Astrosat Space Telescope to collect UV observations that make this possible. In one of our proposals, we generated this plot where we took select regions from this object and repeated the process of fitting in a history to them. The histories are shown in solid curves and color-coded by the areas that they came from in the galaxy. The dashed curves show fits to the same data except without the benefit of the UV. The UV works with the emission lines to provide a joint constraint on the star formation rate and also the current star formation and also the dust reddening. And with the UV punched out of the SED, some of the curves do okay. Like the light blue one, for example, it's not so far off throughout most of the history. But a lot of them, especially in with the low look back times, the recent histories, they actually do pretty badly. So there really is a need for UV space telescopes, which is one of the reasons why I'm, say, for example, excited by ARCUS or the Habitable Worlds Observatory. If with UV capability, they could fill a really, really needed gap. Both Swift and Astrosat are low aperture telescopes, which leaves HST as really our only big UV space telescope. And it would be fantastic to see that change in the near future. Let's look at another example. a lower mass object that's we're going to do the same thing. We're going to decompose its history into its SED into components to work back on its history. And it has a little bit of a different story. Um, I'm going to highlight a little bit of for the UV data here. This is coming from Astrosat now. We are getting the signal to noise that we need in the UV bright areas, although only just. So this is an example where a small aperture telescope can do the work if you sink enough time into it. But this also highlights the benefits and the need for more UV instruments. This is coming from some work that was done by Alison Loney, and so keep your ears open for Loney et al. Probably late 2024, early 2025. Just one of the scientists working on this project. And the UV image on the right, we can clearly see some of the spiral arms in our object. And when we decompose the histories or the SED of this object into different time steps to look at its history, we see that it has a very different story from the first object we looked at. So we do see the center of the galaxy, the core, as active 3 to 5 billion years ago. But it's actually not very active in the first time step. Instead, that clump of material off to the upper left is the most active. So how do we interpret that? Well, remember that we can't unwind the orbital motion of the object. And so there's a couple of things to think about. That clump on the upper left is shaped kind of like an arc, right? And one possible interpretation is that it was actually just a single clump and that azimuthal migration has stretched it out into an arc. That's something that we actually saw with the first object, where some of the bits that were further from the center over time, they get stretched out. And so there's a lot of sort of circular symmetry in the first few time bins. And that's an interesting idea because it would suggest that the first burst of star formation in this object was in this clump that's at a fairly high galactocentric radius now. So one scenario that I find particularly exciting is that this is actually the fingerprint of an accreted satellite. That at some point, this satellite had, say 8 billion years ago, this satellite had a burst of star formation and then maybe didn't do a whole lot since. And it was since accreted into this object and then azimuthally stretched out. This is something we're still working out on the paper. This is only one possible interpretation. But it is intriguing to think that the oldest parts of this galaxy now are maybe not actually in the center, and that might speak to interaction merger history. One of the reasons why that's actually particularly plausible for this object and also intriguing is that this is a case of an LSP galaxy that's not isolated. This one's in a group. So you can see it in this legacy image where up to the top left is a Markarian object. So it's a merging pair of galaxies. And in the UV image, you can see it as the brightest part of the image plane, this sort of white dot above and to the left of our target. And so the way I think of it, this LSP galaxy is a quiet cottage right next to a rock concert. And every now and then someone from the concert, maybe throws something over the fence. It's possible that because it's in a group with other objects, it has a more interesting merger history than some of our others. However, star formation that's off axis is actually a common feature that we see in the present star formation in a lot of these objects. So these are 9 objects in our sample. And out of these, 7 of them show a bright clump of currently star-forming material that's way off to the side. For example, in the upper left is the first object we looked at, and that is, this image is highlighting a region which by itself accounts for 30% of the present-day star formation in this galaxy. And so This is a trend that we see with these objects that the star formation tends to be very clumpy and also far off axis. This is a plot from a paper that I wrote with Miriam Elizer, who's currently a graduate student at the University of Massachusetts, where we looked at several galaxies in H alpha imaging. One of them is one of our targets, UGC 8839. And this is kind of a funny plot that we've isolated the H2 regions within this object and plotted their luminosity as a function of total luminosity within the object, so a fraction of total luminosity. And then we plotted their galactocentric radius as a function of disk scale length. So for that object, how far are they from the center? And the 8839 H2 regions sort of hug the outer upper right envelope of the data points, especially those two data points that are far to the top right, which by themselves, if you add their star formation together, that accounts for 60% of the star formation in this galaxy. So this is a galaxy where 60% of its star formation is occurring at 2 scale radii from the center. This appears to be a fairly common feature of LSP galaxies, and it harkens back to the fitted history that we looked at of the first object, where within the past billion years, most of the star formation has occurred on the outer perimeter. So that seems to be a trend that we're seeing in these objects, that when they form stars, they do so on their very edges. And you might think, well, maybe that's related to gas density. So perhaps the gas density is just very low in the center. After all, H1 gas is, of course, the fuel of star formation. This is an old result where this was H1 imaging, so 21 centimeter radio observations of an LSB galaxy. And they're plotting the black points in comparison to the critical density needed for star formation. And so what they're finding here is that this object basically stays below the critical density of most radii and then sort of pokes its finger above the threshold kind of farther out. And indeed, this object has a ring of star formation at that radius. And this is speaking to a deficiency of H1 at the center of the object, but also because the rotation curve or the critical density depends on rotation, it also speaks to the dynamics of the object. So with this in mind, we returned to the first object in our sample with the VLA and made some VLA observations of it to see, actually, the thing that I was really interested to see in this object was, okay, it's got this recent star formation around the edges. Maybe there is an interaction here too. I mean, it seems to be isolated, but you never really know. And maybe we could see some sort of tidal tails or signs of dynamical disturbances near the edges in H1. Nothing. It's got a very smooth, uniform, happily rotating disk, no signs of distortions or disturbances, no tidal tails. It's pretty clean. But it does have a deficiency of H1 near the center. And indeed, most of the H1 is near the edges. All right, so that brings us to this guy. And those of you who worked with me might have noticed it conspicuously absent from the family photo that we saw earlier. And the reason it was is because if I try to put it on that slide, it looks like this. So this is to scale with the other objects and appropriately plotted. This object is an absolute monster. This is Rubin's Galaxy UGC 2885. And if you want to learn a lot more about this, some of my collaborators, including Benna, are experts on it. This is one of the most massive spiral galaxies in our local universe. It's 5 times as massive as the Milky Way. It has a radius of 250 kiloparsecs. But weirdly, it's a pure disk object where it has maybe a tiny bulge, but if so, it's a small portion of the total mass. And And that's strange because it's in a mass category where most of the objects in that mass category are elliptical galaxies, or at the very, very least, bulge-dominated spirals. Uh, and so you might think, well, that's not a low surface brightness galaxy at all. Well, it has a B band surface brightness of 22, so it's marginally on the edge for our project. But when you compare it to other galaxies in this mass class, this is extremely low surface brightness. So think about it. If you have a category of galaxies which, for whatever reason, tend to form most of their stars on the edges, and they tend to be isolated, so you get very few interactions, and you just let them keep doing that long enough, what do you get? A giant disk that's really expansive and has a higher surface brightness, but not as high as you'd expect for other objects in that mass class. And so partly I'm interested in this object because it does meet the technical definition of being in our category, but also partly because I think there's probably an evolutionary connection between edge-dominated star formation, like we're seeing with these little guys, and these monsters that maybe they eventually grow up into if you let them keep doing their thing for long enough. Even if you're not interested in LSB galaxies, this object is really intriguing because it does sort of stand out in a lot of ways from other objects in its mass class. So we're going to play the same game. We're going to select regions from different parts of this object and try to fit histories to them. And this is what we get. So we see some commonalities where there was a burst of star formation near the center of the object, in this case, very, very strong. The nucleus formed first. We see a general migration of star formation toward the outer disk. But we also see some really strange things in this SED. So for example, in the recent time steps, we do see a kick up in nuclear activity. But one of the things that Bennett has found is that there is evidence for an anemic AGN in the center of the object, implying that there is some ability to fuel the center for star formation and AGN activity. So maybe that's related, but that is actually very unusual for LSB objects. We also see that the outer spiral arms did actually have some star formation at the earliest time steps. It's not zero. And that is actually has the weird implication that this object was always as big as it is now. That if you could go back in time to the epoch, it might have fewer stars back then, but there would be something out at those high galactic centric radii. Now, again, there's always the possibility that this is, in fact, I think it's a very intriguing possibility that maybe this is an accreted satellite that somehow made it into the disk without becoming part of the bulge. But that's something we'll have to look more carefully at. I also want to add that we should take these results here with a grain of salt, because one of the things that we're struggling with this object is getting UV data for it. And so these curves here might have the same kinds of problems that we saw when we punched the UV data out of the SED earlier on. This is a recently accepted result by one of my collaborators, Mateus Carvalho, where he's looking at the H2 content in this galaxy. So this is an object where we are able to see H2. This is coming from the IRAM telescope. On the left, we have H1 contours in red on top of an H2 map. We do see H2 at the center of this object, which is probably fueling the nuclear burst and the AGN. We also see on the right one of the really exceptional things about this object. Remember, it has a low star formation rate. It's a low surface brightness galaxy. But it also has a huge molecular mass, molecular gas mass. And this really does speak to the fact that there is a process, a confluence of dynamics and density that somehow keeps star formation in suspense in these objects. I was very excited by this result because it has actually been very difficult to detect H2 in LSB objects. I ambitiously got 80 hours of IRAM time on one of our smaller objects, and I sank all of it into one object that there was some circumstantial evidence that it had a higher star formation rate and maybe had detectable levels of H2. Nothing. And I'm working on writing up a non-detection paper. So this is, for me, this was kind of affirmation. The optical spectra contain a lot of information, and we can do a lot of other things with that. So this is one of the spectra coming from an H2 region in UGC 8839. And it's partly that it's an H2 region, so of course it has emission lines, but it's also partly that the spectra are deep enough to get signal to noise of 10 on the continuum, which means we get the emission lines really cleanly. So we can do things like chemical abundances. We can do, reddening with these lines. But then we can also do velocity. And this is a low resolution spectrograph, but with enough work and with enough detected lines, you can actually get a velocity field for these objects. And that unlocks the possibility of pairing the star formation history with dynamics. So another little tiny bit of history. In the 1990s and early 2000s, the so-called core cusp problem was at the forefront of low surface brightness galaxy research, where dark matter only simulations, which was the simulations that they could do at the time, suggested that galaxies should have dark matter halo profiles that look like the blue curve here, where it spikes near the sun, or the so-called cuspy halo. Whereas real galaxies show something that's more flat top, the chord halo that we see in red. The solution is really, really cool. So by the 2010s, simulations had gotten a lot better, and they could add things like baryon feedback. And what they saw was that with the right set of feedback parameters, early bursts of star formation in a galaxy would drive gas from the center. Okay, nothing strange there. But the gas would gravitationally drag enough dark matter away from the center to just flatten out that dark matter halo profile and turn a cusp into a core. Okay, great. Problem solved, right? We actually have some agency here to have a look at that, because remember, we have full star formation histories, and some of our objects show sort of a weaker early burst of star formation. And so if this is right, this almost certainly is the answer, so I'm very excited about this, then we should actually be able to compare that to our objects and see the range of halo profiles in comparison to star formation histories. And here's a plot of sort of several of our objects from our sample. We're looking at rotation curves. So rotational velocity versus galactocentric radius in comparison to the Milky Way, where the Milky Way's rotation curve shoots up and then stays fairly flat, so-called classical flat rotation curve. It's very common for spiral galaxies. A lot of our objects are more of diagonal lines, closer to the solid body rotation, the constant angular speed. And a lot of that's coming from the fact that the baryons are more diffuse and letting the dark matter halo dominate at all radii. And so these are actually good laboratories to look at halos, because the baryons have a smaller effect. But then also, because of their interesting star formation histories, they have the ability to test this idea. And so I'll tease this result and say that one of our objects, which has a weak early burst of star formation, seems to have a cuspier halo than a lot of other galaxies. And we're seeing that there is a trend here, which might let us verify one of the trickiest bits of modern simulations. All right, so I'll wrap things up here. Some takeaways. We're seeing a class of objects where the discerning difference is that they grow most of their stars on the edges, which prevents them from developing a high central surface brightness, which makes them hard to detect, but also lets them become maybe eventually these giant disks that we see in Rubin's galaxy. What connection do they have with other galaxy types? Well, they they go through phases of development where they may rise to the level of a starburst. And so if we catch them during that era, they may not be classified as LSB galaxies. Case in point, all those clumps of star formation that we see at the very edges of these objects. And with a range of star formation histories and the ability to quantitatively measure those, we can do things like test baryon halo interactions and sort of get a real world look at some of the neat things that we're seeing in the best simulations of our day. And I'll wrap it up there and open the floor for any questions.
I make a point of not being the first one to ask a question, so somebody else will have to step in.
Any questions from the audience?
Yes, please.
Yeah. Not Benny, you can go ahead.
So I'm asking the question because I thought this was an excellent talk. So we'll have more low surface brightness galaxies in the near future. How much more do you expect? Because that you started the talk with a good like, well, it's not the entire missing baryon fraction, but how you culled your sample from a parent sample, how big do you think that's going to grow with Rubin, for example?
I think that if I can go back to the family photo slide, so within, say, the really, really nearby universe, 10 to 50 megaparsecs, we probably have most of the, if not all of the Milky Way mass class objects in the lower right quadrant. What Rubin will do is let us get down to those depths at greater distances. And I wouldn't be shocked if the number of LSB galaxies in the lower right quadrant, which is the most exciting part for me, grows by a factor of, say, 100 to 1,000 out to 200 megaparsecs.
Anyone else? Yeah, jump in. I have a second. I always have a question. That's
all right.
At all. So the star formation histories, they all assume the fixed IMF, I'm assuming. I mean, if there's nothing else to scoundrel around with, then
that's a really good question. So anytime you hear about fitted star formation history, right? You're at a talk at a conference. The IMF is kind of like the gremlin hiding in the closet. And with this object, we did try changing the IMF and seeing if there's possibly a better fit. And the best fit, I think, was coming from the Miller-Scalo IMF, but the takeaway was that it didn't really impact the history. So we went through the mechanics of refitting the history, and like the exact proportions changed a little bit, but not a whole lot, which was good because the IMF was kind of a nuisance parameter. In some regions, we actually got a slightly better fit to an aggressively truncated IMF, so no stars above 25 solar masses. But the sort of reduction in chi-squared wasn't enough to make it statistically significant. And so that has kind of teased the result that maybe IMF is actually a significant question. And there is a lot of evidence that the AMF varies at least a little bit based on density. So, for example, in elliptical galaxies, which would have formed most of their stars in really high density environments, um, the fitting SEDs to the stellar population that they have shows this sort of excess of low mass stars. And that could imply that in those environments, it's more difficult to form high mass stars. But there's also starburst galaxies where the densities are quite high, and there they're seeing an excess of high mass stars. And the other parameter that would distinguish those two categories is turbulence, where the elliptical galaxies would have formed in a really turbulent environment. So this is a long conversation, and I could do a whole talk about this. But the short answer is it doesn't seem to impact the histories we're seeing here, at least for the few objects we've looked at. But it could be a very significant parameter in terms of understanding the physical differences in the star formation conditions in these objects.
It's because star formation in low surface brightness might be a completely different mode. That's what I was curious about. Coming to that, the fact that it's on the outskirts that you see a star formation, could that be that's where it's connected to the cosmic web, for example? Because you see this in other Hunter et al. In 2011 found something similar with H1 disks, and they used it to find the outermost H2 region. And that was the little thing. So that's the small galaxies in the universe. But it really feels like that could be the contact point where sort of gas flows into the disk. Could that be it? Because then you sort of locally push it over the threshold rather than just one air, just a whole ring, for example, like it was in the Pickering paper.
Yeah, that's the model that I have in mind, where the galaxy is pulling in gas, the gas lands on the outer disk, settles in, and you get a little bit of star formation there, and then it sort of inches its way outward. The question then is, why are the dynamics of these objects not driving the gas further toward the center, the way it happens in a lot of high surface brightness spirals? Well, you do see star formation on the outside, but like if you look at the Milky Way, there's a lot of star formation in our core. That gas is presumably coming from the cosmic web, but it's being slowly channeled toward the center of our object, or our galaxy. The rotation curves probably play a role. So if we have near solid body rotation, then that ends up dropping the shear way down. And so that could partly explain why the gas has a hard time migrating to the center, and why it stays on the edges, and why that sort of simplistic picture of picking off gas from the cosmic web and forming star formation on the edges and slowly building up a disk. That actually works here, whereas other objects like the Milky Way are just more complicated because they can move the gas around radially a lot more easily.
Okay. Cool. Good answer. Okay, come on, people. I don't want to be the only person asking questions, so otherwise I'm going to put Aaron on the spot.
Everyone's tired from staying up last night.
Fair. Okay.
Yeah.
Lovely, but still, science, fun.
We need to think about something beyond our terrestrial worries.
Yeah. So
Very appropriate with your SETI affiliation.
Yeah, the SETI folks are helping to support me in I don't have an image of it, but the new suite of Swift observations we have.
very nice. All right.
Well, I'm sure people will not mind having 10 minutes of their life back. And if you think of anything, of course, you can always reach out to Jason directly.
Please.
And, by email and stuff like that. All right. So we will have our next seminar in 2 weeks by Ryan Sanders. So join us. Of course, you'll get all those reminder emails from me as usual, but it's the same Zoom link in 2 weeks. So see you all in 2 weeks. Bye.